If you've spent more than, I don't know, 5 minutes writing any kind of code, you know one thing to be true. You are going to be wrangling raw text data. I mean, whether you're manipulating names, parsing file paths, validating URLs, or just accepting user input, strings are they're everywhere. And if you're working in C++C, you traditionally hit a major fork in the road. Okay, so let's unpack this. We're diving into how C++ organizes, stores, and lets us modify text. Our mission today is to cut through all that confusion and take the ultimate deep dive into the modern workhorse, the C++ std.string type. And this isn't just some simplistic box for characters, it's an incredibly powerful, feature-rich object with built-in power tools ready for, well, any text transformation job you can throw at it.
That fork in the road comparison is it's crucial. C++ historically relied on the older C string concept, which
Uh-huh.
is, essentially just an array of characters ending with a null terminator. And for anyone who doesn't live and breathe pointers and memory management, that whole approach is it's difficult, it's error prone, and honestly just slow to develop with.
We want the modern, easy, and powerful solution, the one that abstracts away all those low-level nightmares.
Exactly. And the modern approach is the C++ string object, std.string. It lives in the string header, and technically it's defined as a template type called std.basicstringchar. But the key takeaway for you, the listener, is that this variable is an object. And because it's an object, it comes preloaded with dozens of member functions or methods that do all the heavy lifting for you. You access all this functionality using the simple dot operator. It really is the difference between trying to build a custom toolkit from scratch every single time versus just buying a highly engineered multi-tool.
I think that multi-tool analogy is perfect. It really captures the shift in mindset. So let's start with the basics then. What's inside the box? A string variable is defined as a container for an ordered sequence of 0 or more characters. That sequence is defined by double quotes. And those characters are universal, right? Symbols, alphabets, digits, anything.
And since it's an ordered sequence, every single character has a precise internal index, starting at 0. So if you need to access or modify a single element, that index is your key. This is often the very first thing you need to master,
Okay, so if I have a string that's, say, 10 characters long and I want the fifth character,
which be index 4.
right, index 4. We have a clear choice on how to grab it. We can use the simple square bracket notation, index, or we can use the method at index. What's the trade-off there? Because in programming, simple choices like that almost always hide some crucial difference.
They absolutely do. Both methods will get you the character at the specified index, which has to be valid, so between 0 and the string's length minus 1. The difference is safety versus performance. The operator index, the square brackets, that offers raw, unchecked access. It's faster, sure. But if you request an index that doesn't exist, like index 50 on a 10-character string, the result is undefined behavior, which,
Oh.
usually means your program just crashes unpredictably.
The classic segmentation fault waiting to happen.
Precisely.
Yeah.
On the other hand, you have at index, which includes robust bounds checking. It actually verifies that the index you request is valid. If you try to access index 50, it throws an out-of-range exception. And that gives you the chance to gracefully catch the error and handle it, making your code significantly safer and more resilient, especially when you're dealing with user input of unknown length.
So we use the brackets when we are absolutely certain of the index, and we use at when we need that safety and predictability. That clears it up. We should probably also give a quick mention to front and back for getting the first and last characters.
Yes, those are just some nice syntactic sugar for accessing index 0 and length minus 1. But remember, the std.string is also mutable. You can change it in place. You can use that speedy bracket operator on the left side of an assignment to just drop a new character into an existing valid slot. It updates the string without creating a whole new one.
We focused on accessing the internal parts, but what about the string's outer shell? I mean, before doing any major operation, you need to know how big the thing is, how long is the tag.
And that brings us to capacity. You have two methods that on the surface look identical, that length and size. Both return the number of characters. But there's a subtle insight here. While they do the exact same thing for std.string, modern C++ practice really favors size.
Why is that? If they return the same value, why pick one over the other?
Because std.string is designed to behave just like every other standard container dash like a std.vector or an std.list. And all those standard containers use size to report their element count. So by using size, you ensure consistency across all of your C++ code. It links back to that idea that the string is really just a specialized container. And for a quick capacity check, you also have empty, which just instantly tells you if the string has 0 characters.
Okay, so once we know the size, the next core task is traversal. Accessing every character from first to last, probably in a loop. I could use a simple for loop and an index counter, but the sources point toward a more elegant, more powerful solution. Iterators.
Oh, iterators are, well, they're arguably one of those powerful concepts in modern C++ math. They're like special pointers that abstract away the underlying memory structure. For you, the listener, this means the exact same traversal code you use for a string will work for a vector, a linked list, or a map. It completely separates what you are traversing from how it's stored.
So it's all about code portability and elegance. We have begin and end for standard forward movement.
Yep, begin points to the first element, and crucially, end points to one position past the last element. That boundary condition is absolutely essential for stopping the loop correctly.
That makes sense for going forward. But I have to say, I hate writing code that needs to traverse backward. It always seems to involve messy calculations like length 1i. Does the reverse iterator method elegantly solve that pain point?
It solves it perfectly. The std train object gives you where begin, and rend.rearBegin returns a reverse iterator that points to the last character of the string, so the logical start of your reverse journey. And rend points to one position before the first character, the logical end. You write the loop exactly the same way you'd write a forward loop, but the iterators handle all that index arithmetic for you automatically. It's the highest utility way to check for things like palindromes really, really quickly.
Okay, we've accessed characters and we've verified the size. Now let's talk about changing the string dramatically. Let's start with simple growth. If I have hello and I want to get to hello world, how do I add content easily?
The path of least resistance is usually the standard concatenation using the overloaded plus operator. But if you're iteratively building a string, or you specifically want to add to the end, you have three explicit options that offer a bit more control and clarity. You can use pushback for adding a single character, appends RD3R for adding a whole string, or the overloaded assignment operator plus.
That covers simple growth. But text processing often requires, surgical precision. I might need to insert a paragraph in the middle of a file name or delete a section of an HTTP header.
And this is where the precision editing methods come in. First, to completely reset a string back to empty, you just call clear. For insertions, you have fantastic flexibility. You can call insert, index, count char, if you want to insert a specific number of identical characters, say 5 spaces, at a certain point. Or, more commonly, you use insert, index, string to drop an entire string into that position.
And what if I need to delete content?
That's handled by erase, index count. This method removes a specified number of characters count, starting from a given index. These modification functions give you really granular control.
But let's introduce a practical complexity here. I get erase index count, but what if I need to delete a known word, like error, not just a known index and count? Is it overly complex to combine methods to do that?
Not at all. That's exactly how advanced text processing is built. You would use a search function, which we're about to cover, to find the starting index of the word error. Once you have that index, you then use the word's length as the count argument for the erase function. The real power of the string object is in chaining these simple, precise tools together.
Okay, so we are moving into those foundational power tools now. Searching for a specific piece of text, finding the needle in the haystack, is a task every single programmer faces daily.
The primary method for that is find, shrouds the pose. It finds the first occurrence of a substring, and you can optionally tell it to start searching from a specific position. If you omit that position, it just starts at index 0.
But the truly critical insight here is how the string communicates failure. How does it tell you, hey, I couldn't find your needle? It doesn't just return a simple -1 or something.
No, and that's the crucial constant, NMS. If find fails to locate the substring, it returns std.string.npos. To simplify the jargon, NS just stands for index not found. It's defined as the largest possible number the system can represent for a size index, which makes it impossible to mistake for any actual valid index. So it acts as a perfect, unmistakable flag signaling that the search failed.
So the check in your code is always going to be if mystring.find target.std.string.nps. That's an essential pattern to internalize, and if I want to search backward through a really long text log or something...
You just switch to NSO. NSOPO.
Yeah.
That searches for the substring in the reverse direction, starting from your optional position pose.
Okay, now let's talk editing en masse.
Huh.
The search and replace features that make modern text editors so incredibly useful.
This is handled beautifully by replace, index, count, newsecr. This method replaces a segment of the string from your starting index for a length of count characters with the entirely new string. This is the foundational method that powers those high-level text editor features.
And finally, what if I just need to slice out a piece of the original string to work with separately without actually changing the original?
That's subspace count. This is your dedicated slicing tool. It returns a new string object, starting from pause for a length of count characters. And if you strategically omit the count argument, the function just defaults to returning the string from pause all the way to the end. It's incredibly handy for parsing complex data lines.
So we have all these methods to create, change, and query the physical text, but strings are so often just carriers for valuable numerical data. We need to be able to compare them and, crucially, convert them into numbers so we can actually calculate things.
Comparison is pretty straightforward thanks to operator overloading. You can compare strings directly using dir and so on. But here's the insight you really need. The comparison works character by character based on their ASCII values.
So it's not a human language comparison then.
Right. Zebra is actually greater than Apple because the uppercase Z comes after the lowercase a in the ASCII table, even though a might seem smaller contextually. This is exactly why you have to standardize your case, all uppercase or all lowercase, before you try to do any kind of dictionary sorting. Otherwise, capitalized words will always sort before lowercase ones.
That explains a lot of common sorting bugs. Okay, so strings frequently arrive carrying a price, a coordinate, or an ID number. We need to bridge that gap from text to pure data.
This is all about interoperability, and it's crucial. To convert a string representation into a numerical value, C++ gives you the stocks family of functions. For signed integers, you have stoy for standard integers, then stol, and stol for the longer integer types.
And what about for decimal numbers, like currency or scientific measurements?
That's handled by sto and stold, which cover float, double, and long double precision. The key is that these functions intelligently parse the beginning of the string for a valid number and then return the numeric type you need.
And to complete the circle, if I've calculated a result, say 42, and I need to display it as part of a formatted message.
For that, the standard library gives you toString. This handles the conversion of integrals, floating point results, or pretty much any other numeric type back into a reliable string format. It's vital for logging, for display, and for building complex output messages.
Now we get to the highest value part of this deep dive, seeing these methods combine to solve complex problems. Because it's not about just knowing the method, it's about knowing the right combination of methods.
Let's start with one of the examples from the source material, converting between numerical bases, specifically decimal to binary. This really demonstrates the power of building a string piece by piece.
So how does the string object help solve that particular problem?
Well, the mathematical algorithm involves repeated division of the decimal number by base 2, and you collect the remainders until the quotient is 0. So if you calculate the number 13, you get remainders 1, 0, 1, 1. But the first remainder you collect is actually the least significant bit.
Which means the final binary string, 1101, has to be constructed by collecting those remainders in reverse order.
Exactly. You convert each remainder to a character, and then you either use insert 0 character to constantly prepend it to the string, or you collect them all and just reverse the final string using iterators. This perfectly illustrates using string modification methods to build up complex data structures.
And the reverse process binary to decimal conversion is just as illustrative, I imagine.
Yeah, that one requires traversal. You iterate through the binary number string, and for each character you see a 0, 1, you first have to use one of those numeric conversion tricks to turn the character 1 into the integer 1. Then you multiply that integer by its place value 2 to the power of the position, and then sum all the products. It's a flawless combination of string traversal, numeric parsing, and arithmetic.
Let's move to a practical validation problem. The source material outlines the task of checking password strength using a 5-point scoring system. This requires checking for 4 different character classes and 1 length requirement.
And this is a fantastic exercise in applied search logic, specifically using find and that in-post constant we talked about. To score the password, you really just need 4 separate Boolean checks.
Okay, walk us through one of those checks. Let's say verifying the presence of at least 1 digit.
Sure. You would define a standard string that contains all the digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you traverse the password character by character. For each character in that password, you use the find method on your digit string. If the character is found in the digit string, the find method will return an index that is not in post.
So you could write a loop that looks something like for scene. parser. Diff, digits.find, C, EO, score +1 Brady. That uses traversal and the find pose constant perfectly.
Precisely. And you just repeat that logic for uppercase characters, lowercase characters, and symbols. The final point is just a simple capacity check. If askWord.length. This isn't just theory. This is robust, real-world data validation using the object's built-in methods.
And finally, the classic programming challenge. Checking if a string is a palindrome, like madam.
The simple check is pretty easy with reverse iterators. But the advanced challenge is the one that really tests your mastery. Handling phrases like a man, a plan, a canal, Panama, while simultaneously ignoring case and filtering out all punctuation and spaces.
That sounds like a nightmare of manual filtering.
It requires a new, clean string to be built first. You have to traverse the input phrase, and using some external character functions, you check if each character is a letter or a number. If it is, you convert it to a consistent case, let's say lowercase, and then you append it to your new filtered string. Only then do you check the forward and reverse equality of that filtered clean string. It demonstrates that the C++ string object is often the destination for filtered data, not just the source.
What an incredible journey through the capabilities of the C++ string object. I mean, we've covered the safety trade-off of @hell versus the consistency of size over length, the elegance of iterators, that critical failure constant impose, and how to convert raw text into actionable numbers using the Stoy family.
The string object really gives you the precise tools you need to filter and transform any text data. We saw how to combine find and impose for robust password checks, and how traversal is essential for parsing conversions. The true mastery of strings isn't just knowing these individual methods, it's the ability to fluidly chain multiple techniques, like using substruct to isolate a data field, converting that field with Stoy, and then using erase to remove the processed field to automate seemingly complex data parsing problems. It's about turning raw, unstructured text streams into actionable, clean data. What complex text manipulation challenge will you tackle first with these powerful new tools?